मत आइए। Hi guys, can someone please confirm if you're able to hear me? All right, let us get started quickly. So guys, in the previous class, we were talking about trees, binary trees. Today we'll continue the discussion and we'll try to solve some more problems. Okay. So let me go back to. So we were doing mostly recursion based problems in the previous session. I think we solved invert binary tree and then path sum and then same trees. Three questions we solved. Today, let us try to solve questions on some other concept. So I told you in the previous session that mostly when we talk about trees, we talk about tree traversal. I think I was talking about that, right? So we were talking about tree traversal, and we have discussed in terms of tree traversal, we have discussed depth first search, or we call it DFS. Okay. There is another technique which we have not discussed so far, which is called as breadth first search. I gave you an intuition of what is depth first and breadth first, but we did not discuss the traversal. So today let us do a breadth first traversal. I'll tell you what is a breadth first and then we'll try to implement it. And then we will also talk about another concept which is binary search trees. I'll give you a brief introduction to binary search trees and we'll try to solve one problem around that. Okay. So let us talk about what is a breadth first search. And we will do a question on Leetcode. So let me look for the question. Or breadth first search is also called as level order traversal. So binary tree level order traversal. Yeah. Okay. So this is the question we'll try to solve. This is the Leetcode question, but it is also a general concept which we should know. So let us do this one. Okay. So let us first read the question, then we'll try to solve it. Okay. So let us read this Leetcode 102. Okay. Level order traversal is also called as breadth first search. Okay, and breadth first and depth first is a concept that you will come across again when you're learning about graph. So this is a very central concept. We should have a very good clarity about what is depth first and breadth first. So if you remember about our discussion on depth first, let me take an example. Let me first explain what is level first, and then we will level order traversal, and then we will try to think of the code. So let us see. Let us say that we have taken a tree here. Let us say 10, 11, 12, 13. 14, 15, and 16. Okay. So in a depth first search, we go depth. We traverse the entire depth of one branch until we reach the end, and then we go to the when we go to the other branch. Okay. So if we start from 10, we go to 11. Okay. And from 11 we go to 13, and from 13 we'll go to the left child of 13, right? And we'll keep going until we hit none. So after 13 we hit none, so from 10 we'll go to 11, then we'll go to 13, then we'll backtrack to 11, and then we'll go to 14, then we'll backtrack to 10 again, we'll go to 12, 15, and 16. Okay. So we are traversing depth like this. So you can imagine that you are in a maze and you are going till the end where you hit a wall, and then you backtrack and you take explore other possibilities. So that is depth first. What is breadth first? And in depth first, we know that we learned about three different varieties in DFS: pre-order, post-order, and in order. Okay. If you're not familiar with these and if you have not attended the weekend classes, I'll try to put the link to the lecture in the comments. Okay. You can let me know. So if we talk about breadth first search, then breadth first search is not, we don't go into depth, we go to breadth wise. So we take 10, okay, and we explore which are the children of 10. So 11 and 12, okay. And before going to the next level, we explore the entire level. So 10, after 10 we go to 11 and 12. Once 11 and 12 are explored, after that we go to 13, 14, 15, and 16. Okay. So we go this way. If we take the breadth first traversal, then it will be 10, then 11 and 12, then 13, 14, 15, and 16, like this. Okay. So you can say that this is level 1, this is level 2, and this is level 3. Okay. Guys, all of you are following? So how can we do this? So for depth first, for DFS, we were using a stack. Okay. For a breadth first, we are going to use a queue. Okay. So what are we going to do? Can someone tell me in the chat? We'll start with a queue, and for queue we'll take a deck. You know that we have discussed a lot about queue, so we will use a deck data structure in Python to implement a queue. Okay. So we'll start with a queue. We'll start with a queue which will be a deck, and we'll add a root, or you can put it this way. Okay. We will have a root. Root is what? Root is 10. Okay. So we'll add 10 here. Okay. So you know, in a queue we are going to enqueue and dequeue. So this 10 has been enqueued, and when we dequeue, we will be dequeuing from here. Okay. So enqueue will happen this way, and dequeue will happen this way. So we have added 10. Okay. Now what we need to do, we need to explore, all the children of root. Okay. And we need to add them to the queue. Okay. This is our queue. Okay. And we also need to have a result where we are going to store the traversal just like we have done earlier. So we will, let me write this in a different color. So let me make one result, and this result is going to be empty array. Okay. Now we'll say while queue, okay, as long as there is some value in the queue, okay, we are going to take out this node. Okay. We are going to take out this node, and we are going to say for in range. Okay. How many ever values are there? Okay. So we'll take in range size of queue, or let me take the size of queue and put it as a different variable. Let me make it, let me call it level size. Or let me just call it size. And this size is going to be length of this queue. Okay. So for now, what is the what is the size of the queue? Size of the queue is 1 as of now. Okay. And we'll say for number of values which are there in this range of size. Okay. We are going to take out this 10. We are going to take out this 10. We are going to dequeue this 10. Okay. So we'll say node is equal to q dot pop left, or you can say dequeue. This is nothing but dequeue operation. Okay, we have taken out this node and we are going to ask which are the children of 10. So children of 10 are and 12. So I need to add this 11 and 12 to this queue. Okay, so I'll say level dot append node dot val. I will take one level also here. So this level will basically store all the values of a given node, of a given level. Okay, so this is what is level. This is, so I'm running a loop to find out this 10. This is a level. In the next iteration, this will become one level. So basically we want to find out three levels. We want to find out 10. For the first level, we will have 10. Okay, if you look at the tree, the first level is going to be 10. The second level is going to be 11 and 12. The third level is going to be 13, 14, 15 and 16. Okay, this is the result. And our result is going to have value like this: 10, 11, 12, 13, 14, 15, 16. So we will find out this level. Once we have this level, then we will append the level to the result. Okay, guys, is the approach clear? So when we start, we just have the root. Okay, and then we are taking out the root and we are appending the root in the level. So we have this level here and level is having 10. Level now has the value 10. Okay, and this loop is going to run only once. This loop is going to run only once. So this loop is over, and then once this loop is over, we are going to, before ending the loop, we'll add this 11 and 12. So we'll say if node dot left, we will append in queue dot append, we'll say node dot left. Okay, and if node dot right, we'll say queue dot append node dot right. Okay, once this work is done, okay, then we will add this 10. We have this 10, we will add this 10 to our result. This is our result. So we'll say result dot append our level. Okay, and once this whole thing has run, then we will return, for this while loop, we will return result. Now let me give you a dry run of what this code is going to do. Level is going to be an empty array. Okay, so let me now give you a dry run of how this is going to work. So let me clear this queue. Okay, let me clear this queue and let me clear my result. Where is my result? Let me have one result here. And let me have one level also. Okay, this is a very template code. You are going to use this template very often, even in graphs. Okay, we'll say this. So we are starting the queue with a root. So root is going to be, let me take this tree also, put it down. Okay, so the first thing that will happen is that we will have a root here. This is our root. Okay, so our queue is starting with the root value 10. Okay, so we, this is the line, and result is empty. Result is here is empty, while queue level is empty. So we have created the level as empty, and size of the queue is 1. Okay, so this loop is going to run only once. We will take out the node, so node will come out. Okay, and level dot append node, so level dot append node dot value will have 10. Okay, if node dot left and node dot right. Okay, so 11 and 12, 11 and 12 will go in the queue. 11 and 12 gone in the queue, and this loop is over. We will append level to result. This result will come outside, will come here. Okay, in the level of for loop. So we will append this level in result. So we are having this 10 here. Okay, then again, now the length of the queue is 2, the size of is 2, so this size here is 2. It is going to run 2 times. Okay, level again becomes empty, so level again becomes empty. So now we are trying to explore the second level. So we want to have the value of level as 11 and 12, this one. Okay, so let us see if we are able to accomplish that. So the code says node is equal to q dot pop left, so we will pop left, so we will get 11, this line of code. Okay, level dot append node dot value, so we'll append 11 here in level. Okay, if node dot left and node dot right, we are going to append in the queue. So node is 11, so 13 and 14 is going to come in the queue. 13 and 14 is going to come in the queue. Okay, and this loop is not over. One more time it is going to run. So we are going to take out now 12. 2 times it will run, because initially the size of the queue was 2. So we'll take 12, and it says level dot append node dot value. We'll append 12 here, and if 12 is having any children, then we will put that also. So 15 and 16 will come here. 15 and 16 will come here. Okay, this loop has ended. We will come to this line of code. Okay, I hope you are able to see. Let me just remove myself. I hope you are able to. Yeah, okay. Okay, so where were we? We took out 12, and this loop has ended. Result dot append level. So we will append this level to this result. So what will we get? We will get 11 and 12. So if you see, this was our level 1, and this was our level 2, or you can say level 0 and level 1. You can see this is our, see, this is our level 1, or you can say level 0, however you want to count, and this is level 1, and this is level 2. Okay, so level 0 has 10, so we have, in our result you can see 10, and then second level has 11 and 12, so we have 11 and 12. Now the third level has 13, 14, 15 and 16. So let us see if our code will be able to get that. So now the length of the queue is 4, the size of the queue is 4. Okay, and level has again going to become empty, so level is again going to become empty. So let me clear that. Okay, and now again it says node is equal to q dot pop left, so pop left means we will get 13. Okay, 13, and level dot append 13, we will do 13. Okay, and then node dot left, node dot right, it does not have anything, so we'll not put anything in the queue. And again we'll go and we'll pop 14, so we'll get 14. Again same story, we'll put 14 here, and 14 does not have any children, so nothing to do. Again we'll pop 15. 15 doesn't have any children, we'll put 15 here. Similarly we'll take out 16, we'll put 16 here. So level is 16, this loop has ended, and in the result we are going to append 13, 14, 15 and 16. Okay, so this is our final result, and you can see we have gotten our result in the result that we were expecting. It is a nested dictionary which you can clear out later using a simple list comprehension. Did you understand, guys? Breadth, level, order, traversal. I'll explain it one more time without the code. This is the code you can use, but let me explain it one more time. High level, what we did. Okay, code you can write again also. Suppose if we have a tree like this, 1, 2, 3, 4, 5, 6, 7. Suppose 6 also has 8 and 7 has maybe 9. Okay, so we want to do a level order traversal. We are taking a queue. Okay, in the queue we are putting the value, suppose 1. Okay, then we'll see how many values queue has. That many times we want to run the loop. So we want to add 2 and 3 to the queue. We want to remove this 1 and we want to put it in the result. Okay, and we want to add 2 and 3 to the queue, 2 and 3, and this one will be removed. Okay, then we want to take out 2, then we want to pop 2, and we want to add children of 2. We want to pop 2, we want to add 2 here, and we want to put children of 2 here. Okay, so 4 and 5. Okay, similarly we want to take out 3, we want to put 3 here, and we want to put children of 3 in the queue, 6 and 7. Then we want to take out 4, and we want to put it here, and we want to add children of 4 to the queue. 4 does not have any children. Similarly we want to take out 5 from the queue and add children of queue to the queue, children of 5 to the queue. 5 does not have any children. Okay, then we will take out 6, we'll put 6 in the result and add children of 6 to the queue, which is 8. Okay, then we'll take out 7, we'll put 7 here, and we'll put children of 7 in the queue, which is 9. Then we'll take out 8 and we'll put it here. 8 does not have any children. We'll take out 9, 9 does not have any children, and it will come here. If we are using the nested level, then this will come as like this: 2, 3, then 4, 5, 6 and 7, and 8 and 9. Okay, this you can later unwrap and you can get it as a normal list. Are you guys following? Let us now write the code for this. Level order traversal. So what did we decide? We decided that we'll have a queue. So queue will have a deck. We'll use a deck. Okay, and deck will contain the root. So we are starting with a deck. If you remember, when we were doing depth first search, we were starting with a stack. Here we are using a queue, and then we want to have a result. Result will be empty, and then I want to do while queue. Uh, while queue. What do we want to do? We want to create a level. Okay, so level is here, and we want to do level dot append level, not level dot append. We want to find out size of the queue is going to be length of the queue. Then we want to say we want to run a loop for in range length of size, not length of size, just size. Okay, we want to pop the node, so we'll say node is equal to queue dot pop left. Okay, then we want to say level dot append node dot val, so we will put the result in the level, and then we want to put the children of the node in the queue, so we'll say if node dot left, then queue dot append node dot left. Okay, and if node dot right, then queue dot append node dot right. Okay, and once this is done, then we want to add everything to the result, so we'll say result dot append level. You can do extend also. If you do extend, then you will not have to unwrap it later. And once this is done, then we want to return the result. I hope this should work. Let us see. I think I forgot to handle the case where we have none. None type has no attribute val for range size. Under what situation we got this? Okay, you see, this is what I was saying, that you can see where it failed. uh, Let me run it again. It is failing when the tree is empty. So if the tree is empty, then this code is not going to work. See, if the root is empty, then this code is not working. So what we need to do, we need to handle that situation. We want to say that if root is not there, if not root, then return none. Not none, we want to return empty list. You can see in the question itself, the expectation itself is from a nested list. You can see it is, we are giving 3. If you look at the level order traversal of this tree, so we are getting 3 and then 9 and 20 and then 15 and 7. 9, 20 and then we are getting null and null. That is fine. 9, 20 and then 9 is having null and null and then we are getting 15 and 7. Okay, this is fine. No, sorry, null is not there. Here you can see it is 9, 20, 15 and 7. So 9, 3, 9, 20, 15 and 7. This is the level order traversal. You don't have to worry about this null. Null values need not be added in the traversal. Okay, so you can see these are the examples. So if we submit the code, I hope it should work. Yes, it is working. I hope you guys got it. So let me add this question in the sheet. Binary level order traversal. This is a solution. Okay, I'll also add this question in our DSA sheet. Let us do one concept of binary search tree. Let us try to solve a problem on that. Okay, this is the question. Let us try to do this one. This is again a different concept. We'll understand the concept, then we'll try to solve this one. Okay. Or let us not do this one because binary search tree we have not discussed in detail. Let us do a simpler one. Let us say symmetric tree. Let's do this one. This is easier. Let us do this. Question number 101. Okay, guys, let us read the question, then try to approach it. So this is similar on the lines of what we were doing yesterday. So let us read and then try to solve it. The question says, given the root of a binary tree, we need to check whether it is a mirror of itself, that is symmetric around its center. So last time I think we did an invert binary tree. So it is a similar concept. We need to check. We will be given a tree and okay, you see this first. Let us understand the question. See, this is the tree. This is the root. This is the root that has been given. And you can see this is the left child and this is the right child, and they need to be equal, right? And then when you go to the next level, you see this is a mirror image of it. So 3 and 4 and then 4 and 3. So we need to check if this tree is symmetric around this axis. So what approach can we take? Can someone tell me? Given the root of a binary tree, check whether it is a mirror of itself, that is symmetric around its center. Is this one symmetric? Is this symmetric? If we take this, then this is not, this level is symmetric, fine, but this level is not symmetric. It should have been like this, then it would have been symmetric. What we need to do here, can we check if the children are mirror images of each other? If we can check if the right child and left child of one, if they are mirror images of each other, and if they are they can be mirror images of each other if 2 and 2 are mirror images of each other. If this 2 and this 2 are mirror images of each other, and these two can be mirror images of each other if their children are mirror images of each other, right? So can you see the recursive pattern in this? So what can we do? Let me think. Okay, so if, so when we were doing invert tree, what we were doing, first of all, we were checking that both nodes should be present, right? So if this is present, this is not present, or this is not present and this is present, in that case we can return false, right? And if we were doing, if you remember, let us go back to our discussion on invert tree. We can, I think we can use this, we can reuse the same logic. If we go to invert tree, invert tree we were using some other logic. Okay, chalo, we'll do it from scratch. Let me remove this. 101 symmetric tree. Leetcode 101 symmetric tree. And let me take this example. So what I'm thinking is I want to write a function which is suppose def mirror. Okay, and I want to write a function which will take a left node and it will take a right node. Okay, and it will check if these two nodes are mirror images of each other or not. So if you want to check if this root, if this root is a mirror image, we basically want to run, we want to say that if 2 and 3 are mirror images of each other or not. Okay, if 2 and 3, this node and this node, are they mirror images of each other? This we want to check. Okay, so I want to call this mirror function. I want to say that mirror, okay, root dot left and root dot right. Okay, and this mirror function is further going to call itself, because in order to check if 2 and 2 are mirror images of each other, if 2 and 2 are mirror images of each other, we need to check if their children are mirror images of each other, right? So what we want to do first here, if we want to check, okay, we want to first see that if left and right both are not present, okay, what will be the base cases? So I told you, when we write recursion, we have to think about the base cases. And I told you what is the base case. Base case is that situation in the example for which we know the answer. Okay, so for this tree we may not know the answer, but if I draw a tree like this, if I just draw a tree like this 10, so is this a mirror image? Is this a symmetric tree? Yes, it is a symmetric tree. Why? Because its children are null. So if the children are null, then I know what is the answer, right? So I'll say if not left and not right, if both are not present, then I can do a early return here. I can just return true. Also, I know that if left and right, okay, they are not, one of them is not present. If left is there, right is not there, right is there, left is not there. In that case, also it is going to be unsymmetric. Okay, if not left or not right, if one of them is not present, okay, one of them is not present, then we can do a early return called false, right? So suppose if I'm having nodes like this, where I'm having 10 and I'm having 11 here and not nothing here, or if I'm having a node like this where I don't have anything here but I'm having 11 here, in this both situation, this is not a symmetric tree. So I know answer for this situations. So these are my early returns. If this is not the case, if these are not the cases, then what we need to do, we need to check their values. These values should be equal. If left child is present, right child is present, then their value should be equal, right? So if I'll say if left dot val is equal to right dot val, if both of them, if both the values are equal, okay, or not equal, let me say not equal, then I will return false, because I know if they are not equal, then there is no way trees can be symmetric. If all of these conditions are not there, then what do I need to check? I've written all my base cases. Okay, then what do I need to check? If 2 and 2, if I'm saying if 2 and 2 need to be symmetric, okay, if these two have to be symmetric, then what should be the case? What we should do? What we should check? That this tree, this tree, this 3 and this 3 should be symmetric. and this 4 and this 4 should be symmetric, which means that left child ka left child and right child, left dot left and right dot right, they should be mirror images of each other. Okay, and left ka right child and right ka left child should be mirror images of each other, which means this 3 and this 3 should be mirror, and this 4 and this 4 should be mirror. If they are following the pattern, then this 2 and this 2 are symmetric. If this 2 and this 2 are symmetric, then 1 is symmetric, means the root is symmetric. Okay, so what we'll say, we'll just return here if their children are symmetric. But while checking children are symmetric, we need to check, we need to pay attention here that this 3 this 3 and this 3 should be symmetric. Okay, so left child ka left, okay, let me write it, left dot left and right dot right, they should be mirror images of each other, or they should be symmetric and mirror I'm using exchangeably. Okay, this should be true, this should be true, and and mirror, okay, left dot right and right dot left, these two should be same. If both are same, that means, if both are same, that means this left and this right are symmetric, which means this 2 and 2. Okay, this mirror can further call further nodes, because it is possible that we can have nodes here like this, maybe 15, 16, 17 and 18. So this should be what? If this has to be a mirror image, then this 4 and this 4 should be symmetric, right? So this should be how? This should be 18 and 17. Okay, and you see 3 and 3 are symmetric, then this should be 16 and 15. You can see further, for this 3 and 3, you have to check if their 3 ka left child should be equal to this 3 ka right child, and iska right child, which is 16, should be equal to iska left child, which is 16. Then this 3 and this 3 are symmetric, and this 4 and this 4 also should be symmetric. So 4 ka left child should be 17, and this 4 ka right child should be 17, you see, and this 4 ka right, which is 18, and this 4 ka left, which is 18, they are also equal. So which means this tree is also symmetric. I hope you are getting it. So here we are going to return this value, इसको हम लोग return कर देंगे. Okay, and this function will be called. Guys, did you understand? So if you look at the stack here, recursion stack here, first we will call mirror on 2 and 2. ये 2, ये वाला 2 और ये वाला 2 के ऊपर we will call it. Okay, so if we want to, if these two have to be symmetric, right, then this 3 and this 3 and this 4 and this 4 should be symmetric. So in order to do this, in order to check this, we are going to call, first we will call this mirror left left. So this mirror, this will be 3 and 3. Okay, and we will, then after that we will call mirror 4 and 4. Okay, if we are checking this mirror 3 and 3, okay, this is going to return something. If it does not return anything, then it will call, further this 3 and 3 will call mirror of 15 and 15. Okay, this will return value, then we will call mirror of 16 and 16. This wala 16 and this wala 16. I hope you are getting what I'm trying to say. Okay, so this is again a very good recursion wala concept. It's very simple, but you need to spot the recursion. So let us try to solve this symmetric tree. Okay, so we will write this function is symmetric. We'll write one mirror function within this, okay, which will take a left node or we'll just say left and right, left and right. And what were the conditions? If both left and right are not there, if not left and not right, okay, then we can do early return, which is true. If either one of them is not there, which means either if not left or not right, that means it is a false. We'll return a false. We'll say if the values are not equal, if left dot val is not equal to right dot val, then we'll return false. Okay. If all these conditions are not met, okay, that means values are there and their values are equal. Nodes are there and their values are equal. In that situation, what we need to check, we need to return mirror left dot left and right dot right. Okay, which means the left child of left should be symmetric to right child of right node, and mirror left dot right and right dot left. Okay, so this function will basically tell me if two nodes are mirror images of each other or not, and we want to check for the root node. So for in order for the root node to be symmetric, their children should be symmetric. So we'll just say return, or not return, we'll call a function mirror on root dot left and root dot right. Okay, and I will return this. Both nodes are absent. One of the nodes are absent. Okay, this is both nodes present but values unequal. Okay, and this means if the nodes are present and values are equal, then check if the children are symmetric. Let me run this and see. Okay, by the way, what will be the time and space complexity of this one? Time complexity, we are checking every node, so this is going to be O of n. Okay, and space complexity, I told you last time that we are using a call stack. That's why number of times the function is going to be called is equal to the number of levels. So it is O of h. H is the height of the tree. Okay, let me submit it and hope it works. Yes, it is working. So let me take this one and add it in your sheet. Okay, guys, we'll stop here. Two questions only today. I wanted to do some binary search trees, but I think binary search trees, we have to discuss theory, then only we can solve some problems. So we'll discuss binary search trees in our weekend class. Okay. Okay, guys, that's it for today. I'll close the session for today. If you have any doubts or questions, please put them in the chat. I'll try to address it. Thank you.